And this lesson is kind of a unique lesson because we've got kind of two tiers to it. The first tier is we're going to be learning some kind of theory here and doing a couple of simple calculations along the way, but that's not the focus of the lesson. The calculations aren't. The focus is the theory that we're going to be talking about to begin with, and then we're going to be doing a very unique analysis that you're going to need to be able to follow along carefully for non-uniform motion, it turns out, for a lab we're going to do probably tomorrow or the next day. Okay? So this lesson is called Uniform and Non-Uniform Motion. So what we want to be able to do at the end of this lesson is, I believe I misspoke. This is not page 9. This is page 12, correct? Okay. Describe position time graphs for uniform motion, which we already know how to do, and for non-uniform motion. Describe velocity time graphs, which we have not talked about, for both types of motion. And in general, kind of start to bring in the concept of acceleration. Understand the meaning of uniform acceleration. And then this is the big thing at the end, which we're going to be spending a lot of time on, is taking data for an object that's accelerating and using it to find the acceleration of the object, which is not a simple one-step process. So to begin with, remember, this is review, that uniform motion is motion in a straight line at a constant speed. And that statement, everybody, that statement, straight line at a constant speed, is exactly the same as saying constant velocity. We've spent a lot of time talking about this. That since velocity is a vector which includes the magnitude of speed and the direction, if the velocity is constant, if a velocity of an object is constant, it's not speeding up, it's not slowing down, it's not changing direction. That's the textbook definition of uniform motion. And what we're going to end up learning today and talking about more today is we basically have situations where velocity is constant, and we have situations where velocity is not constant. We have that one type of motion, constant velocity, and we have a different type of motion that we analyze, changing velocity. If the velocity of the object is not constant, what we say is that the object is accelerating. Now think about that for a second. If the velocity is changing, the object is accelerating. That's what we say. That's what acceleration means, changing velocity. But it doesn't necessarily mean the object is speeding up. That word, accelerating, even in Science 10, it's not that you're taught something wrong in Science 10. It's just that by the time you get to Physics 20, your understanding of the physics is more sophisticated. In Science 10, they tend to use words like acceleration and deceleration. I think we want to avoid the concept of deceleration here and say, oh, the object is slowing down, so it's decelerating. What we want to say is, if an object speeds up, its velocity is changing, so it's experiencing an acceleration. If an object slows down, then its velocity is changing, so it's experiencing an acceleration. It's a backwards acceleration. It's a negative acceleration. If an object is neither speeding up nor slowing down, but going around, say, a circular curve, its velocity is changing, it's accelerating. And I hope you remember, maybe even on the first day of classes, well, second day, I told you that speeding up, slowing down, and changing direction are the only three situations in the universe where if you're doing it, you know it. You feel it, right? You notice something happening when a car speeds up or slows down or changes direction. But you don't notice if you're moving with a constant velocity. So the human brain can perceive acceleration. So all acceleration means is non-uniform motion. Right? So uniform motion, and I don't even know that this is necessarily in your notes. I'm just trying to highlight the big picture here. Uniform motion is a constant velocity, whereas non-uniform motion is a changing velocity. More specifically, uniform motion means non-accelerated motion. So if you're traveling in a straight line at a constant speed, your acceleration is 0. because there's no acceleration. If your velocity is changing, maybe you're speeding up, maybe you're slowing down, maybe you're changing direction, maybe you're speeding up and changing direction, or slowing down and changing direction. Then your velocity is changing, that's non-uniform motion, and you are experiencing an acceleration. There's an accelerated motion there. And I mentioned on the second day of classes that this separation between the two types of motion is how we start analyzing anything that's moving. In Physics 30, if we're analyzing the motion of an alpha particle in a magnetic field and it's moving in a circular arc, the first question we ask ourselves is the alpha particle experiencing acceleration? The answer is yes, because it's changing direction. Because then that leads us to a set of physics principles we can apply. On the other hand, if it were not, it leads us to a different set of physics principles. So acceleration is the rate at which velocity is changing. Rate at which something is changing. A rate, everybody, is measured by dividing by time. If I say to you that the rate at which I spent money last month, on average, was $140 per day, that's money per day. If the rate at which I eat chicken wings on Friday night is 1 wing per minute, initially, that's wings over time. So the rate at which velocity changes would have to be the change in velocity over time. And if you look at your formula sheet, this formula is kind of on there. It's not precisely written that way. I've given you a formula sheet, have I not? Because we talked about it before. So everybody take a minute and find your formula sheet and get it out. It's not something that we typically have out all the time, but we will. In a few days, we're going to need to rely on the formula sheet quite a lot. So, I want to maybe contrast the formula that we're talking here about with the formula that we've talked about last week. The formula we talked about last week is average velocity is change in position, which, I mean, it actually looks like change in displacement. And for that reason, I said we don't really use it. I want to contrast that formula with the one we're talking about now. And what I told you, everybody, is that for this formula, when we talk about uniform motion and applying it, I tend to just use that as an idea. Because displacement, which is what that D with a vector symbol above it means, that means change in position. Okay? And the delta seems to suggest it means change in displacement, which is not what it means. However, with this formula, we want the delta in there. We don't want to ignore that. I'm not going to worry about the word average. In fact, we may not even talk about that meaning or interpretation of average acceleration until halfway through the course. Okay? We find acceleration by taking the change in velocity over the change in time. How much is the velocity changed by, and then the time. Remember from the first day that delta means change in, and change in means take final minus initial. From this point forward, I will very rarely write this equation for acceleration the way it appears on your formula sheet in any way. Instead, I will be writing this. It's going to be very useful for us to think of that formula that way. The acceleration of an object can be found by taking the final velocity minus the initial velocity and dividing by how much time has elapsed. We don't need to put delta t. That's overkill, I think. So that's the formula. Now again, in your notes, it appears as the formula above it. In your notes, and I'll just keep that frozen on the other screen if you need to look at it for another minute. In your notes, it appears this way. Okay? And I just want you to know that delta v means final velocity minus initial velocity. Now, the vector nature of things is absolutely critical in physics, but not today. Okay? That's what I'm telling you here. I'm telling you that today we're only concerned with the magnitude of the acceleration. We're not really going to be getting into the direction of acceleration today. That's a bigger fish to fry at a later point in time. Okay? We're not going to worry about that right now. So, in other words, if acceleration is a vector and it tells us what's happening to velocity, the magnitude of the acceleration is just telling us what's happening to the speed. Would you agree that when it comes to these two things, they are different? Sukman, what is the thing over here on the left? And what is the thing on the right? Speed. Okay, so this is velocity, and this is speed. Can I write speed this way? Sure. I'm just saying, tell me the magnitude of the velocity. We're back to those absolute value signs. All this means, everybody, is I can either write speed by putting v with no mark on it, or I can write it as velocity and put the absolute value signs. Are you with me? Okay. Now, what is this? Well, this is acceleration. What is this? Okay, here's the thing. We have a special word for the magnitude of velocity called speed. We do not have a special word for the magnitude of acceleration. So what is this? This is the magnitude of the acceleration. And you may think this is being picky, but sooner or later some of you are going to go, wait a minute, well, what do I call that? You call it the magnitude of the acceleration. And it can be written this way. For that reason, when I say we're going to talk about the magnitude of acceleration, because including direction today is too complicated, this is what the formula becomes. Okay? And I think writing that is lazy. It's going to be so important by the time you get to Physics 30 that if you are interested in just the magnitude of a vector, put the vector and put the magnitude signs there. Don't just drop them. Okay? So, can we write for magnitude of acceleration the formula on the right? Yeah, we can. Do I want to? No, I don't. I don't want to, and I don't want you to. So why am I even mentioning it? Because your textbook might. All right. Now, number 2. So acceleration is a change in velocity, and it's defined as being numerically delta v over delta t. What uniform acceleration, wait a minute, don't confuse uniform acceleration with uniform motion. Uniform motion is zero acceleration. Uniform motion, this is the theory part I was talking about at the beginning. Uniform motion, not this. Uniform motion is constant velocity. This is under the umbrella of acceleration. Uniform acceleration means the speed changes by equal amounts over equal time. Jumping the gun just a little bit, if this is velocity and this is time, then this is uniform acceleration. 1 second over, 2 meters per second faster. 1 second over, 2 meters per second faster. Okay? So it's important that you look at the labels of the graph. Today we're only going to be concerned with uniform acceleration. Okay, so today we're not concerned with the direction of acceleration, And we're not concerned with non-uniform acceleration, where the object speeds up and then slows down and speeds up and slows down. We're interested in uniform acceleration. So again, what does uniform motion mean? Constant velocity. Straight line, constant speed. What does uniform acceleration mean? Changing velocity regularly. So, a couple of quick warm-up ideas. An object is dropped from the top of a building, accelerating uniformly from over 5 seconds, reaching a final speed of 49 meters per second. What is the acceleration of the object, and explain the meaning? Okay, so this question does not say find the magnitude. It says find the acceleration. Well, that means we have to use vectors. Acceleration is final velocity minus initial velocity over time. So, what is the initial velocity? Well, it's 0. Now, I admit, I said we're not concerned with direction, but for this warm-up, I'm going to include direction just to begin with, okay? If you drop an object and at that instant in time it's not moving. Now, what is the final velocity? This is VI. What is VF? Well, if you say it's 49 meters per second, I'm going to challenge you to understand why that's wrong. That's the final speed. What's the final velocity? Down, exactly. 49 meters per second down. Now, how do we handle that in a formula? Because the formula has vector symbols in it. And again, I said we're not going to worry about direction. We won't in a second, but I want to include it to begin with. Well, what we do is we say that that is negative 49 meters per second. We say down is negative. Left is negative if we're talking left and right, and down is negative if we're talking in the air. Yep?
Our booklet has 50 meters.
Yeah, it's 50.
No.
Oh, interesting. Okay. Now, I'll change it to match yours. Sorry about that. Yeah, I know why I changed it. Okay. So 50. Let's throw these numbers into the formula. So the acceleration will be 0 minus, 50, negative 50 minus 0 over 5. So VF is negative 50. I'm subtracting VI, which is 0, and it's over 5. This is what I was talking about the other day, that I don't, right now anyway, I don't care about units. We're here to understand the physics. We know what the units are going to be. We can put them in later. So you work that out, and you get negative 10. And the units of this are going to be meters per second, because the top of this fraction was a speed or a velocity in meters per second. The bottom was a time in seconds. Now, if I said, well, what is the magnitude of the acceleration? It would be just 10 meters per second. So, this is a subtle but important idea. If you are asked for the magnitude of something, you don't ignore direction. You include the direction, and then at the end, you lop the direction off. Okay? So, quick math lesson. See how I wrote meters per second and it's meters slash seconds? If you're ever in a math class of mine, that's the first thing I will tell you is mathematically, when you're analyzing things, you never write a slash, you write an over. Okay? So meters per second is this, over seconds. This is what we would call a complex fraction in math, and it's complex because in the numerator of it, there's a denominator. We don't want that. How many of you remember the idea from junior high math that you When you divide by a fraction, you multiply by the reciprocal. Okay? You will be well served if you forget about that rule and use this idea instead. You want to get rid of the fractions denominators that are in the way. You don't want seconds here that I've highlighted, so you multiply the top and the bottom by seconds. And that will cancel those seconds, and I'm left with meters on the top and seconds squared on the bottom. And this is why we write acceleration as having units of 10 meters per second squared. But what does it mean? It means 10 meters per second per second. So if we go by this, the velocity is decreasing by 10 meters per second per second. That's a Science 10 thing. You know that. You should remember that from Science 10. It's decreasing because the acceleration is negative. What would this tell us? It would tell us the speed is increasing by 10 meters per second. Because it's positive 10, and it's not referring to velocity change because it's the magnitude. By the way, the acceleration due to gravity in Alberta here is about negative 9.8. Any questions with warm-up number 1? Okay. This is going to be another case where I don't want to rush things, so we may just get to the end of this lesson at the bell. We'll see how it goes today. Don't worry about it. A plane is flying at a constant velocity of 800 kilometers per hour east for 5 hours, and it can be modeled by that diagram. Does your diagram and the numerical aspect of this question match what I have up here? Now, I don't particularly like this diagram. To me, I find it cartoonish and a little misleading. But the idea is that the plane is equally spaced in all of these, right? It's a plane at different points in time. And the reason it says X kilometers is because from position to position, that's going to be the same. Because the velocity is constant. This is uniform motion. This is not uniform acceleration. So we have to fill in some information, complete the table. First of all, your position table, I think, says meters. It should say kilometers. Well, let's start with the velocity. It will be 800 at the beginning and 800 everywhere else because it's uniform motion. We're back to stuff we talked about last week. What is the position? Well, what we can always do is say, if we're allowed to, it starts at the beginning. It starts at 0. There's no reason why we want to confuse things and say, let's call the initial position 50 kilometers. There's no reason for that. And since it's traveling at 800 kilometers per hour, after 1 hour it will have traveled 800, and now we're back to the concept of uniform motion, that every 1 hour the distance traveled will be an additional 800 kilometers. So we keep tacking on 800 kilometers. 1600, 2400, 3200, 4000. Right, this is, in my Math 30-3 class, we've been spending a large amount of time lately talking about linear relationships. And this is linear because what's happening to your x variable is it's increasing regularly by some constant value, 1 hour. What makes this linear is that your y value happens to be increasing by some constant value in those same intervals. So, let's plot a position time graph here for this motion. Again, this is from last week, you guys. This isn't anything new. This isn't anything new. So we're simply putting 1 hour is 800. I guess we better label this graph. I don't know if yours is labeled or not. What do we want to go up to? 4,000 kilometers? Oh. Why don't we just do that? So each of the little squares is going to be 200. So basically, if we go over 1 hour, we go up 4 little squares because each of those little squares is 200. So we go up another 4 and another 4, etc. I really couldn't care less if you draw that line. I didn't hand out rulers. I guess maybe I will. It'll only take a minute. We're not in a big rush. Would rather we do things nicely than raggedly in a rush. So draw the line. I'm not going to spend class time here picking 2 points on that line and doing rise over run. What will the slope be? 800 kilometers per hour. And this is what a position time graph looks like for uniform motion, which is what this plane is doing. Really straightforward. All right. Just in case you're still catching up here with this diagram, I'll leave it frozen up there on the other screen for you. Now, what about a velocity time graph? Well, let's go 1,000 kilometers per hour up here. Be very careful here because this is not 1,000 kilometers. This graph is velocity as a function of time. And the initial velocity, it's maybe a little unrealistic. The initial velocity is 800 kilometers per hour. It's a little unrealistic because planes take some time to reach a velocity. But we're just talking about the physics of this part of the journey where it's moving at a constant speed. And this number, this velocity, is going to be the same everywhere. I'll straighten these out. So this is what the velocity time graph looks like. What's the slope? What is the slope of a horizontal line?
0.
It's 0. But the slope, everybody, is a rise over a run, which is a change in velocity over a change in time. This is the acceleration. Now, it happens to have kind of non-standard units because it's not in meters and seconds, but it is still the acceleration. It's just that the change in velocity is 0 because it's not changing its velocity. What does the slope of the position time graph tell us about the plane's motion? The slope equals the velocity. What does the slope of the velocity time graph tell us? The slope is the acceleration. And that's going to be a true statement regardless of whether the graph is a straight line that's horizontal or any other line. All right, let's take a look at number 3. This is still under warm-up. A golf ball is dropped from the top of a tall ladder, and the following graph of its motion is constructed. So the velocity downward as a magnitude is given as a function of time. Determine the experimental acceleration of the golf ball. Well, it will be the slope of that line, right? Would you say this is uniform motion? No, because the velocity is changing. Is it uniform acceleration? I would say yes, because it's a straight line velocity graph. So if you take your ruler, do these points lie in a straight line? Well, in other words, my grandpa, pretty near. I mean, it may not be exactly straight, but it's pretty close, isn't it? In fact, I'll just move this down a bit. All we have to do is find the slope of that line. Notice when I drew the line, I didn't worry about the origin. I didn't try to force it through the origin. So you need to take 2 points that you can read accurately. There aren't really any here that I see that I can read accurately, so I'll be doing a bit of rounding, but that's okay. I'm going to go with that one. And I'm going to go with this one. You pick any 2 points you want. You use them to find the rise over the run and get an answer. And I'm going to do the same thing here. Again, these points aren't precisely on readable lines, but I'm going to assume they are. What are we talking about up here? That point, and down here we're talking about this point. If 10 squares is 5 meters per second, 2 squares is 1. I just want to show that to you. That this would be 1, 2, 3, 4, 5. So this is 1.5 on mine, and this is 12.5, 13.5 here. So 13.5 minus 1.5 is 12. My rise is 12 meters per second. Across the bottom, it's the same kind of scale, except that every 2 squares will not be 1, it will be 0.1. So this is 0.1, 0.2, 0.3, 0.4, 0.5. So this is 0.15. And this is 1.55, I got to do this. 1.1, 1.2, 1.3, 1.4. So 0.15 to 1.4. I would have to take 1.4 minus 0.15. (1.25). So this run is 1.25 seconds. So what's my acceleration? The magnitude of it will be the slope of this line, which will be 12 meters per second over 1.25 seconds. I want to say 9.6. Is that right? For my numbers. Now, if you're using the same picture, then you'll get the same numbers as if you pick the same points. But I'm getting about 9.6 meters per second squared. Could we have put that into our calculator and done a linear regression? Absolutely. Any questions with that warm-up? Okay, now we get to the part of the lesson. So this was all kind of about theory, and we'll come back to it tomorrow. Now we come to the part of the lesson where we're going to analyze this data. There's a part A, a part B, a part C, a part D. And I think we will get through this, and then you will have some homework, which will be an example just like this. Can you take a look at this data? It's distance and time, so I'm not worried about direction here. And figure out why we know it's non-uniform motion. Why do we know this object is accelerating in some way? Who can tell me? Gabrielle.
Because the distance or the displacement, which is the y-coordinate, isn't going up by a constant number.
Can you repeat that just a little bit louder, please?
The y-coordinate, which is displacement in meters, is not going up by a constant number.
Right. The times are going up by 0.5 seconds, 0.5 seconds, 0.5 seconds. But in light of what I just said about linear relationships, when we take a look at y, which is our displacement or distance, it goes up by 2.5, and then it goes up by, 6.75, and then it goes up by 11.25. So in later periods of time, it's moving further, which must mean it's speeding up. So what we're going to do is we are going to make a graph of this data. Sketch a position time graph for this data. I'm going to have to leave this frozen on the other screen so that I can refer to it. I've given you the luxury of having everything labeled on here, so we're not going to spend class time doing that. You need to plot all of these data points. Now, I told you in the past that I really don't want us plotting or using 0, 0, but let's do it anyway, just for kicks. So then 0.5 seconds, it's at 2.25 meters. So we got to work out what this scale is. These 5 squares that I'm indicating are 20 meters. They're 20 meters. Which means that each of these itty-bitty squares is 4 meters. Right? 4, 8, 12, 16, 20, 24, 28, 32, 36, 40. So 2.25 meters is roughly 2 meters. It's going to be just half a square above the axis. It's not even worth worrying about exactly where it is. And the next one is 9 meters. Well, that one I can do. 2, 4, 6, 8. 4 rather, 8, 9 is just a smidgen above the second square. 20.25, well, for the purposes of what we're dealing with, let's just call it 20. None of you are going to be able to distinguish on this grid where 20 meters is and 20.25 is. 36, let's see, that would be there. 4 below 40, which is 1 square below 40. The next one is 56.25. So this is 40, 44, 48, 52, 56, well, again, 0.25. You might be able to locate it with a pencil. Me trying to move that dot around on the smartboard is an impossibility. Just make sure that's at 2.5, and it is. And then 81. So that is a quarter of a square above 80. Which is kind of not even worth worrying about, especially since we're not going to draw the graph. You're not going to try to draw a curve, okay? Because we're not going to use the paper graph. 110.25 or something. Let's see. That's 80. This would be 100, 104, 108, 110, 144. Well, there's 140. 1 square is 4, so 144. 182. 182. And at 5 seconds, we were looking at 225. 220, 224, 225. Okay. We're not drawing this to get anything out of it other than the fact that it's not a straight line. Okay. Any questions with plotting the data, though? All right. The slope of a position time graph, always, this is true. This statement that I'm going to highlight for you is always true. Always. If you have a position time graph, the slope is the velocity. Why? I maybe need to change this question. Why is me asking you to use the graph to find the velocity of the race car just a goofy question? Why can we not use that graph, or why doesn't it even make sense to say, what is the velocity of the race car? It's not in uniform motion. So the velocity is changing. All the time it's changing. So the velocity at 1 second is different than the velocity at 4 seconds. And by the way, the velocity at 1 second cannot be found by taking the displacement at 1 and dividing by 1 second. It doesn't work that way. Because if I do draw this curve, and you don't have to, but if I draw the curve, and I'm just going to draw it to there, do you agree that the steepness of the graph at 1 second and the steepness of the graph at 2 seconds are different? Okay, this would be the slope line for 1 second. This would be the slope line for 2 seconds. The slope is continually changing. If you take calculus next year with me, we'll learn how you can do this algebraically. But we can't. We don't know how. So the answer to this question is kind of twofold. It's not a straight line. It's not uniform motion. The velocity, I'm just going to say the magnitude of the velocity is always changing. Yeah, we're going to finish this lesson, and then you're going to have an example which starts off with this part where you have to do the position time graph, okay? So, there is a way for us to get the graph on the calculator, and I'm going to walk you through this, and use the calculator to find the velocity at different points in time. So remember over here where I drew these green lines? There's a way for you to use your calculator to plot this graph on the calculator and ask the calculator, what's the velocity at 1 second? What's the velocity at 2 seconds? What's the velocity at 3? And this is what we're going to do. The first step is going to be to put the data into the calculator. We already know how to do that. Okay, let me grab my calculator. We already know how to do that. We go stat, edit. Now, how many of you have data in there from something else you've been doing? How do you get rid of it? Do you remember? You go to your go ahead.
Second plus and clear all lists.
Right, second plus, which is where you get your memory management menu from. And instead of resetting your calculator memory, although that will do it, just go clear all lists. I'm puzzled as to why I am getting an error. Oh, unarchive. Four. Clear all lists. So now when I go stat edit, it's done. So we want to put this data into our lists. Take a minute and do so. double check to make sure you didn't miss any. And now I'm ready to put in the other ones. One final check of the data. Now there's a lot more, there are more steps here, and you're going to have to know what they all are to get your assignment done today. But I'm recording this, so you'll be able to go and watch it again if you like. So let's take a look at what it looks like. So this is our first step. Get the equation of the graph. That's what we're working on. So how do we look at this data? We have to do two things. You have to turn your stat plot on, and you have to set up your axes. Okay? So second Y takes us to the stat plots, where we can turn this on. Window, everybody, is where we set up the axes. So we're going from 0 to, I think it was about 0 to 6 seconds. Roughly. Let's go up by half a second. And 0 to the biggest distance was, I think, 225-ish. I'm going to go to 250. Up by chunks of 50. Hey, looks good. Okay. So when you do this for your lab, and when you did it last week, we did a linear regression, right? Because it was linear. It was linear. Is this linear? No. So let's go, and I have something in here for Y. Don't worry about that. If you have stuff in for Y, get rid of it. That shouldn't be there, okay? When we did this, you found your regression model calculator under Stat Calc. And what you need to know is this type of graph is called quadratic. It's a parabola, for those of you that have taken Math 20. So we are going to do a quadratic regression. So I go enter, and I am going to want that graph in Y1. I'm going to want to look at that graph on here. Okay. And I know what's going to happen here. I'm going to get cut off by the bell. Okay? So that's okay. We'll get as far as we get, and we'll end it there. So I go enter, enter, enter. Does anybody remember where we find Y1 to tell it to put the equation into Y1? You remember, Maxime? No? Yeah.
Was it in like the vars?
Vars, which stands for variables. Enter Y vars function Y1. Now when I calculate, don't worry about this thing it gives you, okay? Don't worry about it. Worry about the fact that now when you go graph, the graph that it's found matches the data perfectly. Okay, you with me? And we turn the stat plot off. We've used that. We don't want the stat plot on anymore. Here is what it is off. Oh, I turned on my second one. It doesn't matter which one is on. Here is what I want you to come into class having done tomorrow, for tomorrow's class. If you turn the page to page 16. Your homework is to take the data in this assigned problem, plot a graph on paper, then enter the data in your calculator, do a quadratic regression, plot that graph, and turn the stat plot off. So where we're at in our example, I want you to get to in the assigned problem. Tomorrow what I'm going to do is show you how we can find the acceleration from this, which is what we're after. Okay? And then tomorrow we're going to move on as well. I'm sorry for ending the class like that, but I would rather end it here than try to rush stuff through. I'd rather get a good understanding at this point, up to this point. Yep.
You said do it on a separate piece of paper or on the
Does it say do it on a separate sheet of paper?
No, I thought you did.
Did I say do it on a separate sheet of paper?
Yeah.
If I did, I'm mistaken. I didn't mean to use the word separate. Thank you for that. What I want you to do is this question on 16, I want you to do the graph on this piece of paper on page 16 and get to this point in our